Hello everybody. In this lecture, I will be discussing with you about the basics of diode. Our actual topic of discussion as per the syllabus is rectifiers, that is the application of diodes. But before going into that, I will be giving you a little bit basic ideas of what you have acquired during your study in 10 plus 2 level about the basics of the diodes. Now, before going into that, let us have an idea about the terms analog electronics. You know, electronics, this word comes from this electronics word comes from the science of electrons. It deals with the science of electrons. That means how the electrons will move, why they will move, and due to their movement what will be the behavior of different equipments, components, circuits, the operation of it, and thereafter the analysis part. Everything will depend upon the movement or stationary condition of the electrons, especially the movement of the electrons. So the science that is dealt with this the movement of electrons or the mobility of electrons will be called electronics, and the technology that is involved inside this mobility of electrons, and the technology that has been developed because of the movement of electrons is nothing but the electronics engineering. And the term analog especially is an important term as far as electronics engineering is concerned, because you know in these days a term digital is being used everywhere, and this term digital, you are quite acquainted with this term. This digital is meant by something that is related with the appearance or use of digits. That means digital, this comes from some discrete quantities. That means some interleaved point values. More clearly, I can say that between the two successive values there can be an infinite number of values. So there can be a lot of values between two interleaved or successive values. So they are called the discrete values of information. Suppose 1, 2, 3, 4. Between this 1 and 2, 2 and 3, 3 and 4, there are many such values. In fact, infinite number of values. So since they are interleaved, in one apart from other, between them there can be large number of values. So these values will be called the discrete information, and these informations will be helped by the use of digital system. So coming from this digital system, as you are more familiar with this word digital, there is another system, just the antonym of this digital word, that is called analog. So analog word is the antonym of digital word. So in other words, we can say analog means a little more continuous than digital, or rather far more continuous. That means in analog system, between these discrete values or interleaved values appearing successively 1, 2, 3, 4, there can be large number of values that may still exist between them, and they can be used for further processing by the system or some other purpose. So that means an analog system is a continuous system, unlike a digital system, and between two successive values there can be large number of values associated inside it. So in our nature, in our atmosphere, in our neighborhood, most of the signals are of analog type, that is of continuous type, and may take different such instantaneous values. That means at different time instants, different set of values can appear representing that particular signal going all through our neighborhood or surroundings. And once those analog signals are captured by a device called sensor. So we need a sensor, we need a device to capture those analog signals in our neighborhood or surroundings. So these are analog signals that are sensed by that particular device called sensor, and that sensor, the signal that is sensed by that sensor is amplified by a particular amplifier, which is called amplifier, particular device. It may also be an analog device which is called amplifier. And finally, the amplified signal should be processed by an analog system, or if we want to feed this analog signal into a digital system, so between that digital system, if this is a digital system finally, and you know a best digital system is our computer system. So to feed the analog signal sensed by the sensor and amplified by this amplifier into a digital system, we need an intermediate device which is called AD, analog to digital converter. So what it will do a signal conversion from analog form to digital form, so that if that is fed to the digital system like computers, they can be processed by that system, all those signals. So this is the way of how it is done, that the signals in our surroundings or nature or in the neighborhood can be sensed and processed by digital system as well as analog system. So because of this, we need to study both analog and digital systems. So this course is all about the analog system electronics, and how that analog systems or analog circuits can be designed, can be framed, what are the components, what are the basic elements required to frame or to design an analog circuit, or analog, more precisely we can say analog electronic circuits is our concern of study in under the syllabus of this course. So this is the basic idea about analog and digital system and electronics. And now I will be giving you a little bit brief idea about the basics of diodes. So let us see what is actually diode. A diode is nothing but a two-terminal electronic device. The circuit symbol is like this, an arrowhead basically. So it is a two-terminal electronic device. The terminals are named as anode, this side is anode, or alternately called P or positive side, and other side is cathode, alternately called N or negative side. Basically this diode is nothing but, this is the circuit symbol, this is nothing but the extension of the idea of PN junction. So diode is nothing but a PN junction device. That means if you create a junction between two dissimilar type of semiconductor, one is taken as P type and another is taken as N type. I hope you already have an idea, a very good idea about the semiconductors and their types, P type and N type, from your plus 2 level knowledge or study. So if that dissimilar types of semiconductors are merged at a particular place which is called a junction is created. The extension of that PN junction theory is the use of diodes. So diode is diode, that means two, di means two and ode means electrode. Ode, ODE comes from the term electrode. So taking that part of term, that is ODE from electrode, and di means two, that means two terminal, a device that is formed in electronics is called a diode. So diode is basically an extension of the knowledge of the or the theory of PN junction devices. So this is the circuit symbol. Now how this diode will work, let us see some basics about it. Now now you already know the concept of biasing That means how a diode may conduct current through it or may not conduct current through it. To make the diode conduct or non-conduct, we need a particular application of external electrical supply or signal, and that is called biasing. You know two types of biasing for a diode. One is forward, another is reversed. So if we consider the a battery like this, and if we connect a diode with it in this fashion, that means positive terminal of battery is connected to the P side of the diode and negative terminal to the N side of the diode, this condition of biasing is called forward biasing. That means application of external electrical signal to the diode. So this is called forward biasing. The current that is being flown because of this through this circuit, denoted by I, is called forward current. So I is forward current. Similarly, if we reverse the polarity either of the diode or of the battery like this, then the direction of current flow will be opposite, and this type of connection is called reverse bias diode. Now and this current is now denoted by IS, where IS is called reverse current, or better you can we can say it as reverse saturation current, or only reverse current, or leakage current. Now if we plot this voltage and current, voltage across the diode, now if we plot the voltage across the diode V and the current through it based on this forward bias and reverse bias condition, which is called VI characteristics of the diode, VI characteristic of diode, then for the forward bias condition we will see that there is a small voltage. This is the forward direction, positive direction of voltage, and this is the positive direction of current, and this is V, the applied voltage, and this is V, the applied voltage. And during the forward direction, after a certain voltage, still the conduction by the diode is negligible, but when that certain voltage is crossed in the forward direction, the diode current or the current through the diode increases rapidly. Rather, it is said exponential rise. It rises exponentially. In the forward direction, that is in the negative voltage and negative current direction, the diode conducts very lowly. That means very small current will flow. As we go on increasing the reverse bias, the conduction by the diode is very small, but as we go on increasing the forward bias, after a certain voltage, the conduction of the diode is quite large. So this certain voltage, before that, in the forward direction or during the forward bias, this voltage, which is acting as a boundary between a high conduction state of the diode and a low conduction state of the diode, is called barrier potential, or we can say it as cut-in voltage, or also alternately knee voltage. So this knee voltage or the cut-in voltage is equal to a potential, a voltage which is called barrier potential, which is treated as the boundary of a forward bias diode, below which the diode conducts very lowly. That means it is almost in the non-conducting state. No current, absolutely negligible current will flow through it, ideally zero, but after crossing over and above this voltage, cut-in voltage or knee voltage, the diode conducts heavily and the current will rise exponentially. Similarly, in the reverse bias condition, so this side, the right side is the forward region of the operation of the diode, and the left side is the reverse region of the operation of the diode. So, and in the reverse region, as you are going on increasing the current, the voltage in the reverse direction, the current is still negligible. This current is denoted by IS. This is called reverse saturation current or leakage current. This current is because of the minority carriers. You already know this current is because of the minority carriers inside the PN junction device, which is being called here as the diode. So this IS or reverse saturation current is because of the flow of minority carriers only, and no majority carrier is contributing to this current. Similarly, in the forward current, which is exponentially rising over and above the barrier potential or the cut-in voltage, this is because of majority carrier current. You know the concept of majority and minority carriers. So the forward current in a diode is because of majority carriers, and reverse current in a diode is because of minority carriers. And you know the minority carriers, the generation of minority carriers is dependent on temperature, so it is independent of the applied potential, applied biasing, the reverse current, and it is heavily dependent on the temperature. That means as you are going on increasing the temperature, the minority carriers will increase and the reverse current will also increase. So this is the VI characteristic of a diode, you know already. And one thing, as you are going on increasing the reverse bias, the reverse current is very low or very small because of the flow of minority carriers only, and no majority carriers will contribute. But after a certain voltage is reached, suppose here this voltage, at this voltage, after a certain voltage is reached over here, it is being observed that this current will suddenly rises sharply in the negative direction. This voltage, after over and above the current will rise sharply in the reverse direction, is called breakdown voltage. And at this voltage the diode will be destroyed, and this happens because of avalanche breakdown that is being happened in due to avalanche breakdown that is being happened in the diode. And this avalanche breakdown voltage is specific for any particular diode. So you have to be more careful about this breakdown voltage, and diode while working in the reverse bias should be kept inside this breakdown voltage so that the device cannot get destroyed during its operation. So this is the VI characteristic, and because of this VI characteristics, it doesn't look like a straight line, the plot between V and I, and because of this the diode is called a non-linear device. Because of this the diode is called a non-linear device, because the characteristics of voltage versus current through it and voltage across it is not at all a straight line, it is rather exponential, so it is called a non-linear device. Now this barrier potential for a silicon diode, you have to remember, it is 0.7 volt, and for barrier potential for this is for silicon, and this barrier potential is 0.3 volt is for germanium. So you need to remember these two values. This is important for solving problems. Now since we are seeing that this VI characteristics is nothing but exponential, so let us write the equation, the voltage current equation for a diode. If I is the total current flowing through the this diode due to the application of voltage V, then we can write the diode equation as I equal to Is. I is the current through the diode and V is the applied voltage, like this what I have already written. So I equal to Is e to the power or exponential E, this E means electronic charge, EV by eta kt, this is eta kt bracket closed minus 1. This is alternately called Shockley's equation. And the different terms is Is, you already know, it is the reverse saturation current. E is nothing but the electronic charge. V, you already know, the applied external bias or voltage. Eta is specific, it is a property specific to a particular type of diode, whether it is silicon or it is germanium or anything else. K is the Boltzmann constant and T is the temperature across the diode. Now you have to remember the value of electronic charge. It is 1.6 into 10 to the power 1.6 into 10 to the power minus 19 coulomb. This is the value charge of an electron, and the value of Boltzmann constant K is 1.38 into 10 to the power minus 23 joules per K, and T is the temperature in Kelvin. So you need to specify all the parameters in the equation. Now the value of eta for a germanium is 1 and value of eta for silicon is 2, found experimentally, and these are not the exact values, these are approximate values. So you can substitute these during the analysis and the numerical solution purpose. Now let us analyze this equation. When V is positive, the junction is forward biased. Case 1. When V is positive, that means the junction is or the diode is forward biased. FB. And when it is negative, case 2. When V is negative, junction is RB, that is reverse biased. Now if we take T equal to 300 K, that means room temperature, this is the room temperature, and if we substitute all these values in this particular equation, then I can be written as Is e to the power 39, if we calculate 39 by 39V by eta minus 1. So this is after substituting the required values, that is E, K and T, putting E from here, K from here and T as 300K room temperature. Now here the voltage V, this V is nothing but the voltage drop across the junction, that means across the junction of the diode, and this is nearly equal to the voltage applied to the diode, because the bulk resistance inside the diode, bulk resistance means the resistance of the p-type semiconductor and the resistance of the n-type semiconductor taken together is called the bulk resistance of the diode. During the forward bias, that resistance is very less, and that's why the diode will conduct heavily. So if we consider this V as the voltage drop across the junction, it will obviously be nearly equal to the voltage that is being applied across the diode or from the external side. That is, this will be equal to this V, because the drop in the bulk resistance of the diode will be very less during the forward bias. And experimentally it has been found that the range of current over which the diode is operated in the forward direction is quite high, or quite a magnitude greater than the reverse saturation current, that is when the diode is working in the reverse bias. And if we consider the measurement criteria, then the forward current is expressed in the range of milliampere. So forward current will be in milliamperes, while reverse current or reverse saturation current in microampere or even less. So this is all about the mathematical analysis or mathematical representation of the VI characteristics of diode. Now let us see two things. One is static or DC resistance. Static or DC resistance of diode, which is denoted by RDC. This is V and I, ratio of V and I, voltage by current. Now as V and I can vary in the characteristics of a diode, the RDC can be changed or varied. And another expression for diode is dynamic or AC resistance, which is denoted by RAC. The formula is dV/dy, that is incremental change of voltage and incremental change of current. Now take the equation what we have just derived after putting the values of electronic charge, Boltzmann constant, and at room temperature. I equal to Is e to the power 39V by eta minus 1. Now when the diode is quite high in the forward bias condition, that means quite a high forward bias has been applied in the diode, then this term for high forward bias, high value of forward bias voltage, this term 1 will be neglected, because in that case, sorry, there will be a bracket here. This bracket will not be here, it will be here. This term will be neglected, as we can write it like this. E to the power 39V by eta minus Is. So compared with this term will be very much negligible during high forward bias voltage. So that's why we can neglect this one with respect to this rest values. So this equation will be simplified in that case during the forward bias, and if we differentiate this equation to find this dV/dy and accordingly this dynamic or AC resistance RAC, that means if we differentiate this equation with respect to I to find RAC, then we can get neglecting this one during high forward voltage value, so we get at room temperature RAC at room temperature because already we have considered this equation, which is derived in considering T equal to 300 K, that means at room temperature. So RAC at room temperature is equal to, will be found if you calculate, that means simplify by neglecting this one and finally differentiate with respect to I, both side of this equation, you can get RAC equal to, that means this dV di RAC will be eta 1000 divided by 39I, that is eta 26 by I, where I is expressed in milliamperes. As already I have told you, during the forward bias, most of the cases I is measured in milliamperes and RAC, unit of RAC, is in ohms. Now if we consider a germanium diode and putting this eta equal to 1, so for RAC, germanium diode will be 26 by I, putting eta equal to 1. So we can say for this germanium diode, the diode current is 26 ampere for a resistance of 1 ohm. That means if we consider this RAC as 1, then I should be equal to 26 milliampere. So for then if RAC equal to 1 ohm, I is equal to 26 milliampere for that germanium diode operating in forward bias condition. And the slope of the characteristics, what I have just a little while earlier I have drawn, will provide you the dynamic resistance in the reverse direction also, which should be very large. It is obvious because the conduction by the diode in the reverse direction or during the reverse bias is very less, so the dynamic AC resistance will be very large at that part. Here it is less, only 1 ohm it is considered, but in that case during the reverse bias it will be very large. So now let us see one more thing. What is the ideal diode? Ideal diode is something which is nothing but a normal switch. That means it will be having two states, on and off, and the VI characteristics of ideal diode will be like this. The current and voltage will go all along. This is the current during forward bias. It will go all along, it will graze the current axis all along.